talk on joint project we are doing together with Yuri Alpin, Artem Maksayev, and Evgeny Shafeev. Here I'm speaking about positive matrices in entry-wise sense and non-negative matrices in the same. And of course, when we talk about properties of non-negative matrices, we are talking in a way about the properties of related graphs and also opposite. So we could look at these problems as problems about graphs. Vertices, edges, I permit loops, but no multiple edges. And order of my graph is a number of vertices. This is usual language of graph theory, which I'm going to use for it all. So let me just briefly pass. So a walk of length k is nothing but a sequence of edges, of k edges, one after another. A closed walk when start and end points coincide. And I will refer to a cycle as a closed walk with non-intersecting, closed non-intersecting walk. So like 0, but not 8, which is intersect. Okay, and also important parameter immediately rise the length of the shortest cycle. It's usually called years. So there are several ways how you could pass from matrices to graphs. And of course, and here I will be using vertex to vertex matrices. Sometimes they are called adjacent symmetry. So I have H from I to J, from vertex I to vertex J, if and only if the corresponding element at position ij is non-zero.
But then is it 1 because you don't allow multiple edges?
Yeah, here I even wrote Boolean matrix. So yeah, and I could always speak about what is called sign patterns. And thank you. Yes, it's enough to work with once for many purposes. So, and now in graph theory language, I could picturize my matrices, which is nice. So, for example, diagonal elements, these are nothing but loops. And I am working with directed graphs. So sometimes I have only one-way roads. Sometimes I have roads in both directions. So it's just another language, but it is nice language and useful language. For example, let me, before I will go through the details, let me just mention briefly a few important properties which will be useful further on. So there is a notion of decomposable matrix. So I consider permutational matrix, which is nothing but the homomorphic image of certain permutation in matrix algebra, or in other language, matrix with one in each row, matrix such that each row and each column has exactly one non-zero element equal to 1. So the question is, I consider permutation similarity. Where can I get? So in case I could move my matrix to the following block form, where I have considerably many zeros. So here in this block form, matrices B and D are square. It means what it is permutation similarity. I permute rows and I permute columns simultaneously. So I localize, I'm able to localize all zeros in such a way that zero block is so big, so it is touching diagonal, which is important. So decomposable matrices are like this, and otherwise my matrices are said to be indecomposable. Nice combinatorial class, but what it will be in graph theory? Interesting graph theory property is when your graph is strongly connected. So there is an oriented path between any two variables. So it turns out that these nice properties coincide. So here in this theorem, this classical theorem about non-negative matrices, I have the following 4 equivalent conditions. Honestly, 3. So decomposability in combinatorial sense, in the sense I just defined using permutational matrices, is equivalent to this geometric property in terms of graphs. So graph of a corresponding adjoint matrix is strongly connected. So combinatorics, geometry, and algebra. So this condition is saying that identity matrix plus A in a power n minus 1 should be positive. So I could, like nilpotency, I could check nilpotency just considering power equal to the size. And if I have zero matrix, it tells me, okay, your matrix is nilpotent, otherwise not. So here is a similar type condition. And this condition number 4 is just another reformulation of this algebraic condition, because we have this binomial formula, because identity and they commute, and saying this is non-zero is equivalent to say that there exists K such that ij element of K power is positive. So and here again, working with matrices, I could always think about them graphically, like here. So this is indeed strongly connected graph. It corresponds to a decomposable, or sometimes people call it irreducible matrix. Or I could check it algebraically, which is also. So another property, if we go more deeply into this set of decomposable matrices, we arrive to very interesting class, which is called the set of primitive matrices. So my matrix is primitive if I could find, let me start graphically this time. So in the graph, my graph is primitive if there exists a positive integer t, such that I could always get from any vertex to any other vertex by the path of length t.
Exactly length.
Yeah.
And this includes u equal to v?
Yes. Yeah. So primitivity requires this t. It includes with t as an exponent. So this parameter t could be said, we could define exponents, right? But it will be more easy now to understand this property matricially, and especially to answer questions you asked. It will be more easy to look now matricially. So it's always in this series. Sometimes you deal with matrix theory questions, and graphs are explaining you what actually you are doing. And sometimes you are dealing with graphs, and matrices come and doing the job for you. So here it's the same. The primitivity is nothing but the existence of a power such that my matrix is positive. So original matrix is non-negative, and I'm searching for the power which is positive. And once it becomes positive, just by definition of product, once it becomes positive, it is positive forever, which is matricially even more evident. And the smallest such k is of interest, and it is called exponent. And again, there is a following nice characterization. So in my digraph, directed graph, I have primitivity for the graph. I could say that my matrix is primitive, but I could also identify this set of primitive matrices inside the set of irreducible matrices. These are nothing but irreducible matrices or geometrically strongly connected graph in such a way that the cycles lengths have greatest common divisor equal to 1. So again, geometry, algebra, and combinatorics appear together and produce us another interesting class of matrices. And really, it is useful. So you could look for this matrix, and you could easily, well, it could be that your graph is difficult. Sometimes it's just large, and matrices help to see that your graph is not primitive. So like here you see the sequence behaves like this. So it is not primitive, but if I add here just one loop, which results in adding this in northwest corner, I add here 1, then my matrix is primitive by clear graphical reasons, or you could see it just by multiplying. Also good. And of course, I said I'm going to speak about numerical indices related to different matricial properties of non-negative matrices. And some indices appear right away. So again, like working with important matrices, size is a numerical invariance which checks for you if your matrix is nilpotent or not. You just apply the degree function, then you have the answer. Here, you could ask similar question, how I could check if the matrix is primitive, up to which degree we could go in this sequence before my non-negative matrix will be positive. And this is also, this is nice chapter of what could be said combinatorial linear algebra, and it goes back to Wieland. So it turns out that the extremal number is quadratic in the size of matrix, and the maximum of exponent is achieved on this Wieland matrix. So basically, you look to the, you have standard basis, and you make a cyclic permutation on the standard basis. This is what you have. In addition, you put this one here. And that is what is called Wieland matrix. It has extremal behavior.
One thing about the entries of A is the 0, 1 matrix.
Yes. Yeah. So, and moreover, any matrix, it is possible to prove that any matrix of extremal behavior will be permutationally equivalent to this Wieland matrix. But anyhow, exponent is always majorized by the exponent of Wieland matrix. So, well, you may ask why this particular number, why this particular matrix appears here. Again, if you look to graph, it is the proofs will be easier. I am not going to discuss them here, but you just make one for, and it turns out this is everything produced in order to maximize the exponent. Remember, we have this condition on the cycle length that was important. So that is the idea. So this is exponent. It is a very useful notion in many different applications in PDE systems. So it's really important when your matrix will be positive. There is a related notion, and now I again will start from graph theory direction. So it is called scrambling index of my graph is similar numerical invariant. So I am looking for such situation. So it is smallest positive integer, such that for any pair of vertices, I could always find a vertex in my graph, such that I could reach this vertex by the path of length k. So this is, of course, in case of we have Wieland matrix. It turns out that scrambling index has also extremal behavior, and but certainly it is less than exponent. And the question is how to compute. So if I am in the primitive matrix of exponent t, I could always get by the path of length t from any a to any p in my matrix. But here I have very special situation. I need to get from 2 to the special common point. Yeah. So let me look to this diagram here, and let's try to see what happens with this graph. So here, just consider this situation with 2 and 4. There is no other way to get from 2 except by this path, from 4 by this path to the number 1. But I always need to have a certain vertex. So this tells me that the scrambling index is 0. So imagine such a situation with my daughter. I'm going to the park, and there is a gentleman who offers horse riding. So, and he is going through the park with his horse. So my daughter is searching for the horse, and horse is searching for the food. Or we are moving through the park, and the question if there will be a possibility to meet or not. So in that situation here, it seems no possibility exists, because at least in this point, but in this particular point, if we are here and he is here, no possibility exists. But if I add this loop here, he could always wait for us by making these loops around the point 1. So that is basically the idea. And now we could ask about scrambling index. And it turns out that scrambling index is equal to 3, because this will be, it is impossible to get from 7 to 1 in less than 3 steps, but he could wait for us here. And so the minimal number will be 3. Again, this is very useful notion, not only to meet in the park, but for example, in the theory of Markov chains. So people are busy with investigating primitive stochastic matrices. We know largest eigenvalue, but it is important to estimate the second largest eigenvalue. And this is done by so-called Dobrushin coefficient, which is defined here. And good bounds to estimate Dobrushin coefficient are based on scrambling index. So here, using the Dobrushin coefficient, I could estimate the second largest eigenvalue, where k is a scrambling index. This is a nice result of Akelbel. And this is also useful in memory-less communication systems. So again, we'll not go into the details. The idea is you have a certain network. Elements of these networks, they have no memory. So once they receive some information, they could only send it to neighbors and forget. And when new information comes, and assume you bring to this information, I don't know, login and password. And you're asking questions like, if there will be element of network where login and password will arrive simultaneously, and when. And this is a scrambling index, in fact. So many ways actually to compute, but if you do it graphically, it's not always easy. So for example, here, if my graph is primitive, it is equivalent, it is a beautiful result of Levin. Primitivity of a graph is equivalent to strong connectedness and the fact that scrambling index is non-zero. So in case my graph, in case I see my graph is strongly connected, but not primitive, I automatically get that scrambling index is 0. So sometimes it's easy via graph. There are results by, for example, like this by Shannon Lee. You have already some additional, you have symmetry in the graph, and then scrambling index is nothing by the ratio by 2 of the original graph. So once you know the exponent, you could compute the scrambling index. But how to feel algebraically what it means? For this, you need the notion of scrambling matrix. So this notion goes back to Seneca. So scrambling matrix is a matrix such that no two rows of this element are so no two rows of this matrix are orthogonal. In other ways, for any row you could have for any couple of rows you should have a certain column where you both have ones in the first row and in the second row. Scrambling index here is a small is the smallest degree such that you could get scrambling matrix from the original matrix.
Orthogonal? You mean orthogonal?
No, element-wise. I consider them as a vectors, 0, 1 vectors, nothing special.
In the 0, 1.
Yes, for example, I'm dealing with sign patterns. Yeah. So here there are Boolean elements here. Yeah. So again, I'm searching for the smallest power such that I will arrive to scrambling matrix. And sometimes it is easy to compute. It is much easier to compute such power. And it is a theorem by Akelbeck and Kirkland that this is in fact scrambling matrix, scrambling index. So, like, to have certain graph, instead of looking for different possibilities to meet in that park, the park could be considerably large. You just multiply, you just take power sequence of the corresponding adjoint matrix. And you see finally on the step number 3, you see that it is scrambling. So, for example, on the step number 2, on the step number 2, it was not the case, but on the step number 3, for each couple of rows, you have a certain column where both these rows have non-zero position. And you could certainly do these things graphically, but algebraically is more easy. There are other results, for example, for primitive graph with certain number of loops, you have bounds of this form. There is a result including years of minimal cycle, again due to Akelbeck and Kirkland. And the bound is by this function in 2 parameters. For example, for primitive graph, it will give us this the same situation with extreme point as Wieland matrix. And again, Wieland matrix will be extremal matrix with extremal scrambling index will be permutational equivalent to Wieland matrix. So, but what one could be observed, what one could observe, this temperature warning is not from my talk, just in case. It's halfway, so I don't know what will happen, but otherwise there is blackboard as well. So, but it's good, you know, one could really observe that. So in the result of Akelbeck and Kirkland and all these results, we were dealing with primitive matrices, but it's not really necessary to work with primitive matrices. For example, here you could see this graph, this simple graph is not primitive. But still, you could meet in 3 steps when you work in this park. So again, graph not only give us idea how to compute, but give us also idea what to do in more general situations. So, and this is our result with Artem Maksayev. So for any graph with non-trivial scrambling index, actually these two conditions are equivalent. Non-zero scrambling index allows you to decompose your graph in such a case where you have ages in part G1, ages in part G2, and you have only ages from G1 to G2, and this is what we call G1, G2 partition of your graph. If scrambling index is non-zero, this is always possible, and actually backwards. And using this partition, we were able to estimate scrambling index for non-primitive graphs as well. These are the bounds. And it turns out that extremal graphs appear as a natural supplement to this Wieland graph. So you have such a hand for the Wieland graph nearby this word. And this is again, this is the only extremal graph in non-primitive case. Scrambling index could be computed. B is the length of and could be estimated this way. And also this is a bound for scrambling index. And for not strongly connected graph, it could be even improved like this, if you know that your graph is not strongly connected. And again, this kind of graph will give you extremal example. So this is another important invariant, both in matrices, as we have seen dealing with scrambling matrices. In graphs, we were doing a lot, and algebraically. So there is one step further, will give us another important invariance. So remember, in scrambling matrix, we were speaking about couples of rows which are which have elements at the common column. Here, I could speak about more general situation. So these two elements will be called intersecting. So indices I and J are intersecting if they have positive elements in a certain common column. So there is a notion of solidarity. So imagine we are playing chess, and imagine a rook. So if I could move a rook in such a way that I could go from I to J, this is what is called chainable matrix. So now not non-zero common column. Now I could use sequentially such situation by moving a rook, and this defines me what is called chainable matrix. But of course, even among 0-1 matrices, not all matrices are chainable, and so chainable rank is a number of solidarity classes in my matrix. So I'm just using a rook. In case of I could get from any point to any point, I am in rank 1 situation, and this is what is called chainable matrix. Otherwise, I have some classes, and number of these classes will be the rank of my matrix. So again, coming back to scrambling matrices, if my matrix is scrambling, of course it is chainable, but certainly not the other way around, because, for example, here, those who play chess immediately see that one could go from row 1 to row 3. Row 3 could be from row 3 to row 4. Row 4 intersects with row 2, but I couldn't find, but it is not a scrambling matrix, since row 1 does not intersect with row 4, because just zeros are in different positions. So we received a nice index, nice combinatorial index. And it turns out that the name rank was actually suitable here, because really it behaves like rank in many different situations. For example, we have Frobenius bound for the rank of a product, and we have even Sylvester law bound for this chain rank, for this number of equivalent classes with respect to a root, and all other consequences. I will not go into the details, but I will use now, will illustrate why this function is interesting. So we extended it combinatorically, but our definition came from combinatorics. But now I'm planning to use it in generalizing algebraic results. So there is a classical result of Frobenius theory about Frobenius form of non-negative matrix. And this result is classical, but we could move one step further, and we could try to deal with Frobenius type results for matricial semigroups. And this is already, this was a question for some time, but let me first define important invariants to deal with matricial semigroups. So if a certain power of my matrix is chainable, then I will call my matrix potentially chainable. So in a way, it replaces primitivity. So it's a generalization of primitivity where I deal with positive matrix finally. Here I am dealing with chainable matrix. So it is positive up to the rook I have on the chessboard. So of course, primitive matrix is potentially chainable, but not the other way around, as the following example shows. But let's say if I am on the set of strongly connected graphs, or in algebraic terms, if my matrix is decomposable, then primitivity is nothing but a potential chainability. One goes. And now back to Perron-Frobenius theory. So primitive matrices are among those strongly connected graphs. So for primitive matrix, we have positive eigenvalue, which is a simple root of characteristic polynomial. We have this inequality, and we have positive vector corresponding to maximal eigenvalue. So lots of nice things, more than so if this is for primitive, but if I am in more general class of decomposable matrices, then there is a notion called imprimitivity index of my matrix. This is this goes back to the following result by Frobenius. So my matrix is either primitive, my decomposable matrix is either primitive, or could be decomposed using primitive matrix in that special form. And this H here, the number of blocks which I could find by using this permutation similarity, is exactly the imprimitivity index of my matrix. Very nice result of Frobenius. And now I'm introducing more combinatorial indices to show how to proceed with. So here it is for one matrix, but what will be the structure of, let's say, matricial semigroups? And it turns out that there is some structure, and this was discovered at first by Protasov and Voinov. So they introduced the following notion of decomposability. So matrix semigroup is called decomposable if for any indices I and j, I have a matrix in my semigroup such that in this matrix entry on corresponding position is non-zero. So remember, in a decomposable matrix case, we had similar property. So it's natural. And by the way, decomposable semigroups could be, so there are decomposable semigroups without decomposable matrices. For example, this one, generated by these three matrices, is decomposable, but these three matrices were not decomposable.
So the semigroup is under multiplication.
Yes, yes. I am using usual matricial multiplication.
Yes.
not the other products up to now. Yeah. So semigroup is primitive if there exists a positive matrix in my semigroup. So again, it is natural in a sense that remember, primitivity is when the certain power was positive. So here it means that if I consider cyclic semigroup generated by one matrix, this will be primitivity index of a matrix, will be nothing but primitivity index of my semigroup. But it turns out to be a correct generalization in the general situation. And there is a generalization of imprimitivity index. So we deal with non-zero positions, which are pairwise non-intersecting, and we are looking for the biggest gamma such that I have a basis where these supports are pairwise non-intersecting. It turns out, again, that this decomposability index for non-decomposable matrices for strongly connected graph is nothing but a decomposability index, imprimitivity index for a matrix for the corresponding matrix. I will not go into the details. I just want to mention that there is a structure of a semi-group here. So there is a definition of when a matrix here by Pn, I consider matrix which has a semi-group of matrices without 0 rows and 0 columns. This is one of the assumptions. So when it acts like a permutation on a certain partition, I say that it is a corresponding permutation. So the semi-group, this is still a result of Protaska. So semi-group, matricial semi-group, which satisfies the condition that 0 rows and 0 columns are absent, and irreducibility in the sense I just mentioned, irreducibility for semi-group. So the following three conditions are equivalent. First, it does not contain a positive matrix. In primitivity, index is greater than 1. And remember this block type structure. So when I say about partition, I am saying that operators could be reduced to certain homogeneous-like form. So for the lack of time, I will not go into the details here. So it is good theorem in many different sense, but in particular, it allows me not only to reduce matrices in a certain special form, matrices from irreducible semi-groups, but it allows to find, for example, polynomial algorithms to consider, like I have a family of matrices, I want to realize if there exists a positive product of this in this family, for this family. And it gives me polynomial algorithms as a consequence. So these results are of interest. And but what could be done for in case we avoid irreducibility? So there is another notion of solidarity relation now in semi-group. So again, intersecting for two indices in a semi-group means the existence of a matrix where these two indices are intersecting. And so solidarity relation for two elements means that consequent indices would be intersected in a certain particular matrix. So again, this is certain relation, certain equivalence relation on the partition, and two indices are in solidarity relation exactly in the case when in the corresponding cyclic semi-group we have solidarity relation for these indices in the power n-1 for generator. So, and finally, we have result using this. Previously, it was decomposability index, and now in solidarity index allows us again. So here we only assume non-existence of 0 rows and 0 columns. And using, remember this Frobenius result, where original matrix was decomposable, and you reduced it to a certain block form with primitive matrix. Here you have corresponding result for potentially chainable matrix. Again, there is a certain block form for your semi-group. And so even for one matrix, even if you are dealing with one matrix, it is a new result because you could permutation, so your matrix could be reduced to certain block form, where blocks are not primitive, but potentially chainable. So all elements of your semi-group would be reduced this way. Yeah, we'll not concentrate on this more. There are some other generalizations, but as everybody today was speaking on preservers, I decided to include some other results of related nature about maps preserving some of these indices and properties. So let me just mention about scrambling index. So scrambling index is invariant. We already discussed from 3 different points of view. And preserving is just this condition here. Of course, it's not like positivity in any sense, but this is just a number. But same questions appear. What are the maps? And there is a whole theory of such maps, which goes back to Frobenius, who considered linear bijective maps preserving determinant and characterized them completely via this standard form. And when it was generalized by Schur, who was working with minors, when it was generalized by Dieudonné, who was working with singular locus of determinant. So singular matrices are mapped to singular matrices, and you ask what are the maps. And in many situations, standard maps appear. Some technique, even going back to Dinkin, could be used here, because from one side, you have certain set or invariant, it is invertible for example. And so it belongs to here. If you deal with invertible maps on n by n matrices, your semi-group, which fixes certain property, belongs to here. But from the other side, it contains a certain natural example, which you could just guess what are they. And the question is, in this tower, if you can prove that there is nothing, there is no option for to be a proper subgroup in this tower, then you're in business. And this could be done from many different, by many different techniques, in particular by Dinkin, classification of maximal subgroups of classical groups. I will not go into the details. There are many results here, depending if you consider equivalence, relation, certain number, like we are considering many techniques. But let me just mention, so if we have preserver bijective additive operator, which preserve non-zero scrambling index, then together with Artyom, we were able to prove that the following result is true. So always there exists a permutational matrix such that your map is like this. And in case
additive means linear, or just
additivity is enough. But so in case you could consider diagonal and off-diagonal parts separately. And here is the complete result. So for additive bijective map, depending on the scrambling index, on the value of scrambling index, if it is 0, you have this kind of characterization. If it is 1, you have little bit more maps. And if it is extreme, you have a certain sum where you act permutationally on diagonal, and off diagonal parts separate. So there are different other characterization results, but in particular, the result I like is that you could actually prove bijectivity. So I remember back many years ago, Charlie Johnson was on one of my talks, and he said to me, well, I'm not surprised by the characterization, but always I am surprised if you could prove that by preserving properties, assuming preserving properties, you could prove if your map is invertible or not. So here it is not, it is rather technical, but it is possible to show that this is always a bijective map. We'll not go into the details. We'll just mention finally, why these indices. I already mentioned several applications. Just want to mention one more. So there is a notion of finite automaton. Like if we use our credit card, want to take cash from the credit card, we are dealing with finite automaton, as in many other situations. So of course it is important if you come to use ATM, it's important that not depending on what previous client done to the machine, it will say to you, please insert your credit card. So so it's always a question, how to get to the same point after any situation which could be done to finite automaton. So I was speaking already about matrices, graphs, combinatorics, but there is another language. When I draw such a nice park, I also speak on finite automaton, right? Because this is nothing but directed graph is nothing but finite automaton. So I could always ask about synchronizing word. So for example, here, if I take this word and ask to move along the corresponding edges, it always brings me from any place. I think it will bring me to the place number 1. So you could just experiment by your own. So whatever previous client did, I could still come and it tells me, please insert your credit card. So, and of course the question, you could, you could ask about satellite rotating near the moon satellite. After coming back from that side of the moon, you should send a signal. So it will again go to the usual setting. So it's important to economize. The length of this word should be economized. And it's well-known Cherny conjecture about the minimal length of synchronizing word of a finite automaton. So Cherny suggested some nice machines, finite automatons, with extremal slowly synchronizing machines. But he also suggested that they are indeed extremal. So his conjecture, which is still open, tells that these are the best machines. But the bounds which exist up to now are of cubic order, to compare with quadratic order here. And it turns out that using exponent and using scrambling index, you could really produce slowly synchronizing finite automaton. I will stop here.